Hello. In this section, we will continue talking about exponentials and logarithms, and specifically we'll go over some techniques on how to solve various types of equations that involve exponentials and logarithms, and work out a series of examples. So we'll start with exponential equations. First of all, some exponential equations can be solved by using what we call the equivalence property of exponential expressions. This is the equivalence property. Let's say that if b, x, and y are real numbers, and if b is greater than 0 and not equal to 1, and then let's say that we have an equation that equates two exponentials of the same base. B raised to the power of x equals b raised to the power of y. The equivalence property states that if the bases are the same, then the only way that could be true is if the exponents are also the same, right? So if b raised to the power of x is equal to b raised to the power of y, that implies that x has to equal y. The exponents have to be equal to each other. So if you can rewrite an exponential equation in such a way that the bases are the same on both sides of the equal sign, then you can apply this property. Let's look at a few examples to illustrate how this might work. Hang on a second, let me get my pen going here. So this first one, 5 raised to the power of 3x minus 1 equals 125. Well, kind of a careful look at that. I can see that 125 is the same thing as 5 cubed. Okay, so I could rewrite it in that way. Now the base is the same on both sides. The only way this could be true is if the exponents are equal to each other. So I can just equate the exponents and solve for x, and the solution to this equation would also be the solution to the original exponential equation. This is a pretty simple linear equation. Add 1 to both sides to get 3x equals 4, and then divide both sides by 3 to get x equals 4/3. So there's an application of the equivalence property. Similarly, over here, I've got 1/4 equals 8 raised to the power of x. But with a little bit of manipulation, I can rewrite this equation so that both sides have the same base. So for example, 1/4 could be written as 1 over 2 squared. 8 could be written as 2 cubed, right? So that's 2 cubed raised to the power of x. 1 over 2 squared could also be written as 2 raised to the power of -2. Here you multiply the exponents, so you get 2 raised to the power of 3x. So now I have rewritten the equation so that the base is the same on both sides. Now I can just equate the exponents. Oopsie, sorry, try that again here. That should be a -2 right there, not a -3. Okay, here we go. -2 equals 3x. Okay. And then divide both sides by 3, you get x equals -2/3. Okay. One more along these lines. Let's say we have 8 raised to the power of x plus 3 equals 4 raised to the power of 5 minus 2x. Well, 8 could be written as 2 cubed. Okay, so that's 2 cubed raised to the power of x plus 3. Of course, 4 could be written as 2 squared, right? So that's 2 squared raised to the power of 5 minus 2x. And then I can multiply the exponents here. So that gives me 2 raised to the power of 3x plus 9 equals 2 raised to the power of 10 minus 4x. Now the base is the same on both sides. Now I can just equate the exponents. 3x plus 9 is equal to 10 minus 4x, and solve this. I could start by adding 4 to both sides, which gives me 7x plus 9 equals 10, and then subtracting 9 from both sides, which gives me 7x equals 1, and then divide both sides by 7, so you end up with x equals 1/7. Okay? So that's the equivalence property, but this property only works if it's possible to rewrite both sides of the equation using the same base. Many exponential equations cannot be rewritten to have matching bases. So to solve these equations, what we can do is we can use properties of logarithms to solve. Let's take a look at how that would work. For example, 2 raised to the power of x equals 7, right? So what would you do here, right? Well, you could, it's not really at all clear how you would take the number 7 and rewrite that as an exponential with a base of 2, right? So the equivalence property is not really feasible here. But what you could do is you could take a logarithm of both sides of this equation, and you can choose a logarithm of any base, but it really only makes sense to choose either natural or common logarithm, since those are the types of logarithms that your scientific calculator has a key for, right? Let's choose a natural logarithm. If I do ln of 2 raised to the power of x equals ln of 7, right? Now I can apply the power property, and the exponent x can be brought out front. So x times ln 2 equals ln 7. Now I can solve for x by dividing both sides by ln 2. X equals ln 7 divided by ln 2. This you can plug directly into your calculator using the ln key on your calculator and evaluate. And if you did that, you would get approximately 2.8074. Okay. So that is the technique that you would apply when you cannot use the equivalence property. Let's look at another example. Okay. 3 raised to the power of negative 0.02x equals 0.07. So again, if I choose something like a natural logarithm, ln of 3 raised to the power of negative 0.02x equals ln of 0.07. Bring the exponent out front, so I get negative 0.02x times ln 3 equals ln of 0.07. And then to solve for x, you just divide by everything that's not x over here, right? So you divide by negative 0.02 ln 3. And so when you solve for x, you'll end up with x equals negative ln 0.07 on top and 0.02 ln 3 on the bottom. But once again, you can just plug that directly into your calculator and evaluate, and you get about 121.0281. Okay. Let's take a look at this one. 4 plus 3 times e raised to the power of 2x equals 11. First thing that I would do here is I would isolate the exponential term by subtracting 4 from both sides. If I do that, I'll be left with 3e to the 2x on the left and 7 on the right. And then I would also divide both sides by 3. So I get e to the 2x equals 7/3. Okay. Now, for many of these, it does not really matter if you use a natural logarithm or a common logarithm when you take the logarithm of both sides. But in this case, it makes the most sense to use a natural logarithm because the exponential has a base of e, right? And a natural logarithm is a logarithm with a base of e. So a natural logarithm will make it simplify down much quicker. If I do ln e to the 2x and set that equal to ln 7/3. And when we covered some of the basic properties of logarithms earlier, we said that if you take a logarithm of an exponential, and if the logarithm and the exponential have the same base, then the result is just the exponent. So on the left, we just have 2x. On the right, we have ln 7/3. And then solve for x, you divide both sides by 2, right? ln 7/3 divided by 2, which you can plug into a calculator, which gives you approximately 0.4236. Okay. And we'll look at one more exponential equation before we move on to talk about logarithmic equations. This one is a little bit more complicated, right? Because we've got two exponentials that are equal to each other. They have different bases, and the exponents are linear expressions. So once again, we'll have to choose. We take a logarithm of both sides, and my preference is natural, but base 10 is also just fine. But I'll do ln of 2 raised to the power of 3x minus 2 equals ln of 3 raised to the power of 2x plus 1. Okay. Now on both sides, I apply the power property. The exponents come out front, right? So on the left, I've got 3x minus 2 times ln 2 equals 2x plus 1 ln 3. And then I got to solve this for x, and I'll start by distributing the logarithms on both sides. So on the left I have 3x ln 2 minus 2 ln 2. On the right I have 2x ln 3 plus ln 3. Then I want to rearrange terms, put everything that has an x on the left, everything that doesn't have an x on the right. So that means this 2x ln 3, I'll subtract that from both sides, and 2 ln 2 I'll add to both sides. When I rearrange those terms, I will get 3x ln 2 minus 2x ln 3 equals 2 ln 2 plus ln 3. Then on the left, we'll pull out a factor of x. So I get x times 3 ln 2 minus 2 ln 3. On the right, I've got 2 ln 2 plus ln 3. Finally, I can solve for x by dividing both sides by the quantity inside the parentheses there. So I get x equals 2 ln 2 plus ln 3 divided by 3 ln 2 minus 2 ln 3. This can be plugged directly into your calculator, right? Since everything is in terms of a natural logarithm, which we have a key for. And if you plug that in, you're going to get approximately negative 21.0973. Okay. So that is a few examples of exponential equations. Let's talk about some logarithmic equations now. And we're going to limit our discussion to equations that can be written in this form. Equations that are a mix of logarithms and constants, and all the logarithms are of the same base. When that's the case, then it will always be possible to collect all the logarithms together and write the equation such that you have a single logarithm on one side of the equation and a constant on the other side. It might take a little bit of work to rewrite it in that form, but once you do, then you can take the logarithmic equation and rewrite it in exponential form to solve for the variable. Okay. Few examples of equations of this type. Okay. This one right here, log base 5 of 3x plus 1 equals 2, right? With this one, it's already written in this form. We have a single logarithm on the left and an exponent on the right. So I can just rewrite that in exponential form, right? So we have 3x plus 1 is equal to 5, right, raised to the power of 2. 5 is the base and 2 is the exponent. And then I can solve that for x. So I get 3x plus 1 equals 25. Subtract 1 from both sides to get 3x equals 24. And then divide both sides by 3 to get x equals 8 as your answer. Okay. Over here in this next one, what we see is difference of two logarithms on the left is equal to a constant 2. So the first step would be to consolidate the two logarithms into a single logarithm using the quotient rule of logarithms. I can write that as log base 3 of x plus 6 over x minus 2 is equal to 2. And then I can rewrite this expression in exponential form, right? So I have x plus 6 over x minus 2 equals 3 squared. Or x plus 6 over x minus 2 equals 9. Then I can multiply both sides by x minus 2, and I will get x plus 6 equals 9x minus 18. And I can solve that for x. If I subtract 9x from both sides, I get negative 8x plus 6 equals negative 18. If I subtract 6 from both sides, I get negative 8x equals negative 24. And then if I divide both sides by negative 8, I get x equals 3. That's my answer. Okay, let's do this one here. We have log. Figure out where my pen is here. Oops. Sorry. My pen upside down. Okay. Log x plus 15 equals 2 minus log x. So first step is I will add log x to both sides so that the left side of the equation has all of the logarithm terms. That will give me log x plus 15 plus log x equals 2. Now I can use the product property of logarithms to consolidate the two logarithms on the left into a single logarithm. That gives me log of x times x plus 15 equals 2. And now I can rewrite this in exponential form. Log this is a common logarithm, which means it has a base of 10. So I get x times x plus 15 equals 10 squared. Or if I distribute the x, I get x squared plus 15x. 10 squared is equal to 100. So I get the quadratic x squared plus 15x minus 100 equals 0. And then we solve that, choosing a method of your choice. Probably the easiest is factoring. This quadratic factors into x plus 20 times x minus 5 equals 0. So the two solutions to the quadratic are x equals negative 20 and x equals 5. But we have to be a little bit careful, because sometimes when you end up with a result like this, where we have a quadratic, there are two apparent solutions, but those may not necessarily both be solutions to the original equation. Back when we first discussed logarithms, one of the things we talked about is that you cannot take the logarithm of a negative number. The domain of a logarithm is restricted to positive numbers only. So there's no way you could take the logarithm of negative 20. It's undefined. So negative 20 is actually not one of the solutions. So the only solution is x equals 5. Okay. And let's try this one here. Log base 4 of x squared minus 9 minus 3 equals log base 4 of x plus 3. We'll go ahead and rearrange terms, put the logarithm terms on the left and the constant on the right. So that will give me log base 4 of x squared minus 9 minus log base 4 of x plus 3 equals 3. Then I can use the quotient property to consolidate both of these logarithm terms into a single logarithm, which will give me log base 4 of x squared minus 9 over x plus 3 equals 3. And then I can rewrite that in exponential form. I will get x squared minus 9 over x plus 3 equals 4 cubed, or x squared minus 9 over x plus 3 equals 64. And then we proceed from here. Now, the easiest way to go from here is to recognize that x squared minus 9 can be written as a difference of squares. Specifically, that can be written as x squared minus 3 squared. Okay. And the reason why that's important is because when you have something that can be written as a difference of squares, you can factor it as, in this case, x minus 3 times x plus 3. And then I've got an x plus 3 in the denominator. And this simplifies down because now I can cancel out this x plus 3 here with this x plus 3 here. And I end up with just x minus 3 equals 64. And then I just add 3 to both sides, and I get x equals 67. So that's the general technique for solving an equation of this type, is you find a way to rewrite the equation so that the left side of the equal sign is only a single logarithm, the right is constant. Then put the equation in exponential form and solve for the variable. We'll wrap up this section by going over a couple of application problems. And this first one is revisiting compound interest, which we covered a couple sections ago. But now that we have some new skills and we know how to apply some of the properties of logarithms, we can take the compound interest formula and we can solve it for something in the exponent, such as time or rate. And in this case, we're going to use the equation for continuous compounding. So here's our question. If $20,000 is invested in an account earning 2.5% interest, compounded continuously, determine how long it will take the money to grow to $45,000. Round to the nearest year. So we want to say, how long will it take for the $20,000 to grow into $45,000? So $45,000 is the money that we end up with, so that's the value of A. A is equal to 45,000. Okay. 20,000 is the money we start with, the money that we invest, that's the principal, so that's P. 2.5% is the interest rate. We want to express that as a decimal, so 0.025. And now we'll plug these numbers into the formula right here. So I get 45,000 equals 20,000 times E raised to the power of 0.025 times t. And our goal is to solve for t. I'll start by dividing both sides by 20,000 to isolate the exponential. So 45,000, so I'm going to get 45,000 divided by 20,000 equals e raised to the power of 0.025t. Now when you divide 45,000 by 20,000, the result is 2.25. Like so. Now, the easiest thing to do in this case would be to essentially rewrite this in logarithmic form. The exponential is a base of e, so the logarithm will be a natural logarithm, so it's ln of 2.25 equals the exponent, which is 0.025t. And if I solve for t, I'll do that by dividing both sides by 0.025. So I end up with t equals ln of 2.25 divided by 0.025. And that you can plug into your calculator and evaluate. You get about 32.4. It says to round to the nearest year, so we'll round to 32 years. So it would take approximately 32 years, a little bit more than 32 years, for the $20,000 to grow into $45,000 under these conditions. Okay, one more example here. The following formula relates the energy E in joules released by an earthquake of magnitude M. What is the energy released by a magnitude 6 and a magnitude 7 earthquake? Okay. It says, as a comparison, a 1 megaton nuclear weapon would have an energy release of 4.18 times 10 to the 15 joules. That's 4.18 followed by 15 zeros. And the eruption of the volcano Krakatoa in 1883 produced an energy release of 2.09 times 10 to the 19 joules. So those are a couple of reference points for us. So let's figure out the energy release of a magnitude 6 earthquake. So we've got the equation log E equals 5.24 plus 1.44. Magnitude 6 means we replace m with 6. We want to solve for E, which is the amount of energy. If you take 1.44 and multiply it by 6 and then add that to 5.24, you get 13.88. And then this is something I can rewrite in exponential form. I have E, log is a base 10 logarithm, so E equals 10 raised to the power of 13.88. And if you evaluate that, you're going to get approximately 7.6 times 10 to the 13 joules. Okay, so 7.6 followed by 13 zeros. Then let's do something similar, but for a magnitude 7 earthquake. So I would get log E equals 5.24 plus 1.44 times 7. This simplifies into log E equals about 15.32. And if I rewrite this in exponential form, I'll get E equals 10 raised to the power of 15.32. And if you plug that into your calculator, you'll get a result that's about 2.1 times 10 to the 15 joules. Okay. So, yeah, 2.1 followed by 15 zeros. So, one thing that is interesting about this is basically then exploring, well, how much more powerful is the magnitude 7 earthquake, right? So one way we could do that is one way we could do that comparison is by taking the more powerful earthquake, which had 2.1 times 10 to the 15 joules, and divide that by the less powerful earthquake, which is 7.6 times 10 to the 13 joules. That gives me 2.1 over 7.6. 10 to the 15 divided by 10 to the 13. You subtract the exponent, so you get 10 squared, which is really 2.1 over 7.6 times 100. Which equals 210 over 7.6. And let me just plug that into my calculator real quick here. Calculator, 210 divided by 7.6. About 20, if you round that to the nearest whole number, it's about 28. So what that tells you is that a magnitude 7 earthquake is about 28 times more powerful than a magnitude 6 earthquake. And that's an interesting result because what it illustrates is that a magnitude scale that's typically used for measuring the strength of an earthquake, it's measured on what we call a logarithmic scale, which means that, if somebody said, if talked about a magnitude 6 versus a magnitude 7, you might think, oh, those earthquakes are fairly similar in strength, right? Because 6 and 7 are numbers that are pretty close to each other. But the way the scale works is that a difference of one magnitude is very significant, right? That means the earthquake is 28 times more powerful. So it just illustrates how that works. So for this section, that is it. So we'll go ahead and wrap it up here.